Now we can do some practice for our alpha substitution reactions. Recall for most of these that fairly straightforward. We're deprotonating at the carbon next to the carbonyl and then adding whatever electrophile is present. Typically, one of the most challenging steps is just the determination of which carbon of the carbonyl, which alpha carbon the addition takes place at if the carbonyl is not symmetric. And that's what we see immediately in part A. We have LDA, strong base, generally irreversible, and we have low temperature. Those are both conditions that favor the substitution occurring at the less substituted carbon. So our electrophile here, which is a methyl group, will end up on the less substituted carbon. Part B, our carbonyl is not symmetric either, but it doesn't really matter in this case. Why not? Well, if we look at the left side of the carbonyl, that alpha carbon, there are no hydrogens there. Since there's no hydrogen there, we can't form an enolate on that side, and any alpha substitution that's going to take place here has to happen on the other side. Again, our electrophile is a methyl, and so we can see that the result is the addition of that methyl group. All right, part C, we have a more complicated looking compound, but the pieces that make it look, strange, this lower part, turns out they don't really do anything here. Again, this is an alpha substitution reaction. It has to take place either at this carbon or at this one. Just like part A, we have an irreversible base, low temperature. That means we're going to favor the less substituted carbon for this substitution. Slightly different electrophile, but same reaction overall. Part D is very similar to part B. Again, we have one of our alpha carbons, this one here, that has no hydrogens. So that means that we know the substitution has to take place here. Only difference is our electrophile has two halogens, one at each end. And so that's going to end up meaning as long as we have enough base, and I haven't specified that the amount of base here is limited, and as long as we have two hydrogens on our alpha carbon, we can get two substitutions to take place, and we can actually, by doing that, form a ring through this alpha substitution. Part E, the addition of hydroxide and bromine to a methyl ketone. This is the haloform reaction, where we can convert a methyl ketone into a carboxylic acid. Remember, that takes place through three separate substitution reactions. So that methyl group has three hydrogens on it. We can deprotonate it 3 times. Each time gets a little bit easier. And after we've done all 3 of those, we end up with this CBr3 group, which doesn't look like a great leaving group, but turns out it's just good enough that hydroxide can trigger an acyl substitution reaction, and we get the carboxylic acid. Part F is one of our rearrangement reactions that we learned. This is the one where we're essentially approximating for acetic acid, and our electrophile, the methyl iodide, ends up getting substituted on to the acetic acid that we were essentially hiding by using this malonic ester. Question 2, we have a set of pairs of uh, ketones and or aldehydes, and we want to know which one will more easily form an enolate. So in part A, we have acetone on the left, and then we've added a bunch of carbon groups on the right. We know that the more we add carbon groups to it, the more electron donating it is, the less reactive the carbonyl. Part B is pretty straightforward. Part B, we have one compound, the one on the left, benzophenone, that neither one of the alpha carbons has any hydrogens on it. Since there's no alpha hydrogens on it, not only would it be difficult to enolize, but it would be, in fact, impossible to enolize because there are no alpha hydrogens. So if our question says more easily enolized, this is the only one that can form an enolate. In part C, we have the ketone versus aldehyde. We know in general that aldehydes are more reactive because of less donating groups, and so that will be able to be enolized more easily. All right, questions 3 and 4, we have a couple of mechanisms to look at. Again, we're working with LDA at low temperature. That tells us we're going to form an enol at the less substituted carbon. Or in this case, since we're under base conditions, we should more accurately say that we're going to form an enolate, since there's nothing that's going to protonate to ever give us the actual enol. Now, in this question, we don't actually have a separate electrophile. Nothing else is being added. However, there is that bromine elsewhere in the molecule, and so our enolate can reform the carbonyl, and then those pi electrons can attack internally and kick out the bromine. And so we've managed to form a ring here. Question 4, we're going to take a look at something very similar to what we saw in 1D. So if you weren't quite sure why we got that ring to form in 1D, this is not the exact same example, but it's extremely similar, and we'll be able to give you a more detailed explanation here. So again, with LDA, we're going to deprotonate to form an enolate. And then that enolate reforms the carbonyl and gives us our initial product. So we've now added a 5-carbon chain with a bromine left at one end. And if we now form another enolate, from more base being present, that resulting enolate, that we form here in this second step. Ran out of room, so we'll just imagine that we know the bromine's there. Enolate can attack that. Kick out the other bromine, closing down the ring and giving us our product. And let's fix that, because the actual product here, given that we're dealing with LDA, should be coming from the less substituted enolate. Finally, question 5, we have a short synthesis. You can see that basically there's 3 things that we need to do. We need to add in a methyl group on the left, methyl group on the right, and then convert the carbonyl into an alkene. We know we can convert that carbonyl into an alkene in a single step. We can do that using a Wittig reaction. And then each of those methyl groups can be added in an alpha substitution reaction. We add the first one. In that case, it doesn't really matter what conditions we use, because the molecule is symmetric, so we could just use LDA and methyl iodide. In the second step, we've got to be a little bit more careful, because we want to select for the less substituted alpha carbon. So LDA, low temperature, and methyl iodide will complete our synthesis.